So far we discussed a number of interesting topics under process control part, and in the next phase we will discuss advanced control schemes. Under the advanced control scheme, today we will discuss the systems with large dead time. So, our topic is systems with large dead time. Fine. And this is under advanced control schemes. Now, a closed loop process consists of a number of dynamic elements like the process, the measuring device, the controller, the final control element. A closed loop process includes a number of elements. One is the controller, the final control element, the process, and the measuring device. So, if we connect all these elements, we obtain the closed loop block diagram. This is the closed loop block diagram. Almost all the dynamic elements may include time delays. Almost all dynamic elements include time delays. Like time delay is involved in transportation of fluids over long distances. See here, controller, final control element, process and measuring device construct the closed loop block diagram. All these dynamic elements may include time delays. Like time delay is involved in transportation of fluids. Transportation of fluids over long distances. Fine. Time delay is involved in transportation of fluids over long distances. This is related to which element? This is related to the process. Time delay is involved in sampling and measurement. Time delay is involved in sampling and measurement. It is obvious in this closed loop block diagram that the controller needs output information y. The controller needs the output information y. Now, that information we can get by collecting the sample and that then measuring that sample, fine. So, that takes some time. Therefore, we can say that the time delay is involved in sampling and measurement of y. So, this is related to which element? Measuring device. This is related to measuring device. Similarly, time delay is involved in developing the actuating signal. Time delay is involved in developing the actuating signal, and this is related to the final control element. This is related to the final control element. Time delay is involved in human controller. Time delay is involved in human controller to think and take proper control action. To think and to take proper control action. And obviously, this is related to the controller. Now, in all of the situations noted above, the feedback controller would provide unsatisfactory performance due to the presence of dead time. In all the above situations, the feedback controller would provide unsatisfactory performance due to the presence of dead time. And we will discuss few other reasons which are related to the dead time, like the effect of disturbance is detected after a long period of time. So, the effect of disturbance is detected after a significant period of time. Why the controller provide unsatisfactory performance? We are discussing the reasons. First reason is the effect of disturbance is detected after a significant period of time. Second reason is the controller calculated the control action at present time step based on the last measurement is not adequate. Next is the controller or the control action calculated at present time step. Based on the last measurement. Is inadequate. See, the controller calculates the control action at present time step based on the last measurement. Originally, this is not the last measurement due to the date time. This is actually the measurement some steps back. So, this is originally not last measurement, this is some steps back, measured signal which is some steps back. Therefore, the control action is not adequate for the existing situation. Third one is the control action also takes time. To make its effect. Felt by the process. These are the reasons for which the feedback controller would provide unsatisfactory responses. In the next, we will take one example to observe the effect of dead time. In the next, we will consider one example to investigate the effects of dead time. Consider the open loop transfer function given as Kc exponential of minus TdS divided by 0.1s plus 1. This is the open loop transfer function which we considered earlier. Fine. Now, Td crossover frequency and ultimate gain. If Td is 0.123 which we considered earlier, we can easily calculate the crossover frequency 17 radian per minute. If Td is 0.123 minute, then crossover frequency is 17 radian per minute. This we can calculate, and the corresponding ultimate gain is 2. Fine. Similarly, if we increase Td to 0.236, then the crossover frequency is reduced to 10 radian per minute, and ultimate gain is also reduced to 1.4. If we increase further Td to suppose 0.535, then crossover frequency is decreased to 5, and ultimate gain also is decreased to 1.1. This data we obtain based on this open loop transfer function. Fine. Now, it is very obvious that with the increase of Td, the crossover frequency and ultimate gain both decrease. So, with the increase of Td, crossover frequency decreases. It means the closed loop response is sensitive to lower periodic disturbances. It means the closed loop response is sensitive to lower frequency periodic disturbances. This is the first observation. Secondly, with the increase of Td, ultimate gain decreases. That means we are forced to select Kc value low value we have to select. I mean we need to reduce Kc to avoid instabilities. Fine, because ultimate gain is the maximum value we can take. So, if Ku decreases, we have to select lower value. So, if we select lower Kc value, then what happens? The response becomes sluggish. If we decrease Kc value, then the closed loop response becomes sluggish. So, these are the effect of dead time. So, due to the presence of dead time, we observe that the closed loop response or the control performance is degraded. Therefore, there is a need to devise a dead time compensator. Fine. So, our next topic is the derivation of dead time compensator. Dead time compensator. For deriving the dead time compensator, we will consider a simple closed loop block diagram. The block diagram looks like this. This is a controller block. We are assuming Gf and Gm both are 1. This is the process. Fine. So, this is the process. This is the process. So, this is the closed loop process for servo case. Fine. Now, we assume here that all the dead time is caused by the process. Here we assume that all the dead time is caused by the process. Fine. Usually we consider we denote Gp to represent the process. So, here Gp is equal to Gs multiplied by exponential of minus Tds. This is the dead time free part, Gs is dead time free part, and this is the dead time part. Fine. So, this is the transfer function of the process which we consider in this block diagram. Now, the open loop response we can write as ZOL, which is equal to y m bar divided by y set point bar, and this is written as Gp, Gf, Gm, Gc, multiplication of 4 individual transfer functions. This is the generalized form of open loop transfer function. Fine. We know all these individual, we know the expression for all these transfer functions. Substituting those, we obtain y bar. Here y m bar and y bar both are identical, because we have considered Gm equal to 1. Then we obtain Gc, Gs exponential of minus TdS y set point bar. This is the expression for output response y. If we substitute all the individual transfer functions in this equation, we obtain this. Now, it is obvious that this is delayed by time Td. It is obvious from this expression that it is delayed by tau d minute. Now, what is our aim? Basically, if this information y bar is fed back to the comparator, our target is to give dead time free response to this comparator, so that the controller is not affected. Fine. Now, if we consider this is the ideal response, I mean if we represent, anyway first I am just mentioning the aim. Aim is to remove this dead time part from the input signal to the comparator. This is our aim. Aim is to remove this dead time part from the input signal to the comparator. Fine. So, ideally the response should be Gc, Z, y set point bar. Agree? This response includes this dead time part. We have to devise the comparator so that the input signal to the comparator does not include this dead time part. So, if we represent the ideal response by y star, then y star should be Gc, G, y set point. Now, how we can obtain this y star? We can obtain this y star, this is suppose y star, and the information which is coming from process through direct measurement, that is y bar. We are just adding something with this y bar so that we can obtain y star. Anyway, I am just drawing this figure. This is GC, this is our process that includes date time part, this is y bar, this is comparator, y set point, our target is to give y star information to the comparator. But originally we are getting y bar, fine, but we need to give date time free response to this comparator. How that is possible? Suppose we are adding another signal denoted by y bar with this y to obtain y star. So, it is straightforward to calculate this y prime. I mean y star is basically the summation of y and y prime. Y star is known to us, that is GC Z multiplied by y set point. Y is GC Z exponential of minus TDS y set point. So, what will be this y prime? That we calculate, that will be 1 minus exponential of minus TDS multiplied by GC Z y set point. So, if we add this expression with the expression of y, then only we can get date time free response, which can be fed back to the comparator, fine. Now, we need to include this expression in this block diagram. How we can do that? You see, we can write this expression further as y prime divided by y set point, which is equal to GCG. So, if this is the output and this is the input, then the transfer function can be represented by this expression, and this is nothing but the transfer function of the date time compensator. This is the transfer function of the compensator. Output of the compensator is y prime, input is y set point, fine. Now, we will just include this compensator in this block diagram. So, this is the block diagram, this is the expression for compensator, this is the block diagram. Output is y prime, input is y set point. So, I am writing here 1 minus exponential of minus TDS. Can I connect this block like this? Output is y prime, which is equal to this multiplied by z, this is z, multiplied by GC, this is GC, multiplied by y set point, this is y set point. Can we do this? No, we cannot do this, because the actual process includes z and this exponential term. In the actual process, we cannot separate, I mean we cannot get information from the actual process excluding this date time part. So, this is not correct. We can connect like this. Then you see in the expression output is y prime, then this part which is written here multiplied by GC, this is GC, multiplied by G, we can write here G. Fine. So, this block represents the date time compensator. This block represents the date time compensator, and this compensator was proposed by O. J. M. Smith. This was proposed by O. J. M. Smith. Therefore, sometimes it is called as Smith predictor. It is also called as Smith predictor. Fine. So, we obtain the block diagram for the compensator, Z compensator. Output is y prime and input is y set point, which is represented by GC, Z, 1 minus exponential of minus TDS. Fine. Now, in this expression Z and TD are involved. Now, G is the process model and TD is the date time. So, the date time compensator depends on the accuracy of process model as well as the value of date time. This date time compensator depends on the process model represented by Z. This also depends on the value of TD. We can get perfect compensation only if Z and TD are exactly known. We can get perfect compensation if the process model and TD value are exactly known. But in practice, this is never known exactly. So, they are known approximately. Fine. In practice, both the process model and TD are known approximately. If that is the case, then we will represent the approximate model as Z prime and the approximate TD as TD prime. Fine. We will represent Z prime for the approximate model and TD prime for the approximate date time. Then what will be Y star? We know Y star is Y bar, which is the actual process output, plus Y prime, which is the output of date time compensator. Y bar is GC Z exponential minus TDS. This is Y bar, and how much will be Y prime if G and TD are not exactly known? We can get from this equation, from this block. Y prime will be 1 minus exponential of minus TD prime S multiplied by GC Z prime, and this will be multiplied by Y set point bar. Agree? Just in the expression of Y prime, we considered TD prime and G prime in place of TD and G. Rearranging this, we obtain GC multiplied by Z prime plus Z exponential of minus TDS minus G prime exponential of minus TD prime S Y set point bar. Rearranging, we obtain this expression for Y star. Fine. So, what conclusion we can make based on this expression? When we can get perfect compensation? We can get perfect compensation when G equal to Z prime and TD equal to TD prime. I mean, when the process model and the date time value are exactly known, then only we can get perfect date time compensation. The larger the modeling error, that is Z minus Z prime and TD minus TD prime, the less effective is the compensation. The larger the modeling error represented by G minus G prime and TD minus TD prime, the less effective is the compensation. Fine. Third remark, which one is more crucial on the date time compensation? I mean, error in G or error in TD has severe effect on date time compensation. TD, because it is related to exponential term. So, this is more crucial to the date time compensation because of the exponential function. fourth remark. See, in this date time compensator expression, TD is considered as a constant quantity, but sometimes this TD may vary with time. Sometimes the date time TD may vary with time, that is not taken into account in the date time compensator expression. So, that is you can say one drawback. Next, we will discuss the date time compensation and the effect of error in TD. Next, we will discuss date time compensation and the effect of error in TD. We observe that there may be the possibility of error in both G and TD, but we are considering only error in TD. So, for this purpose we will consider the process represented by Gs exponential of minus TDS, which is again 0.1 s plus 1 exponential minus 0.53 s 535 s. Fine. To discuss this topic, we are considering this transfer function to represent the process. See, this is the transfer function of the true process, I mean this is G. So, this is true transfer function of the process. Obviously, Gs is 1 divided by 0.1 s plus 1 and TD is 0.535. It is obvious that Gs is 1 divided by 0.1 s plus 1 and TD is 0.535. We will consider P only controller. So, controller transfer function we can write as Kc. This is P only controller. We will consider here both Gm and Gf equal to 1. For simplicity, we are considering Gm and Gf both are 1. Now, we will consider 3 different cases. In the first case, we will consider there is no compensator. Case 1. In case 1, we consider no compensator. Fine. The open loop transfer function which we are considering is represented by Kc exponential minus 0.535 s divided by 0.1 s plus 1. Fine. This is given to us. So, based on this transfer function we can calculate the corresponding crossover frequency, that is 5 radian per minute. In fact, this problem we discussed previously and we obtained the crossover frequency 5 radian per minute. Corresponding ultimate gain is 1.1. Fine. So, what value of for Kc we can select? We have to select the Kc value lower than 1.1. Fine, because this is the ultimate value at which we get sustained oscillation. So, for stability we Kc should be less than 1.1. For stable response, we have to select Kc lower than 1.1. If that is the case, what will be offset? Maximum value we can select for Kc, that is 1.1, fine, at which we obtain sustained oscillation. If that is the case, what will be offset? The expression for offset for the example system we can derive as 1 divided by 1 plus Kp Kc. This is the expression for offset for the example system, fine. So, if we substitute the values, then we obtain 1 divided by 1 plus how much is Kp? 1. How much is Kc? Suppose we are considering 1.1, then it is 0.48. It is a large offset. If we consider the maximum value of Kc, that is 1.1, then we obtain the offset 0.48. Say this is time, this is y, this is suppose 1. So, this is the offset. Which is equal to 0.48. That means the corresponding value is 0.52. So, this is closed loop response with Kc equal to 1.1, fine. So, this is case 1. If we do not use date time compensator and if we use the maximum permissible Kc value, that is 1.1, we obtain offset 0.48. Next we will consider case 2. And that is perfect compensation. In case 2 we consider perfect compensator. It is true when z prime is equal to z. Perfect compensation is possible when z prime is equal to z, that means process model is perfectly known. Secondly, this Td prime is Td, that means the date time value is exactly known. For the case of perfect compensation, y star by y set point is equal to Gc z. I mean there will not be any date time part. So, how much is this one? Kc divided by 0.1 s plus 1, agree? There is no date time part. So, for perfect compensation we get y star by y set point equal to Kc divided by 0.1 s plus 1. Now, this is the first order transfer function. This is the transfer function of a first order system Kc by 0.1 s plus 1. Is there any crossover frequency? No, because if we vary omega from 0 to infinity, we obtain the variation of phi from 0 to minus 90. So, there is no existence of crossover frequency. If there is no existence of crossover frequency, then we can use any large value of Kc. We can use any large value of Kc. There will not be any instability problem. Fine. Since there is no existence of crossover frequency, so we can use any large value of Kc. Suppose this value is 100. Since there is no instability problem, we are considering large value of Kc, and that is 100. If Kc is 100, what will be offset? 1 divided by 1 plus Kp Kc, that is 0.01. Fine. Without using date time compensator, we got 0.48. With using perfect compensator, we are getting insignificant offset. This is insignificant offset. Fine. But we mentioned that in practice Z and Td, they are not known exactly. So, that we will consider in case 3. In case 3, we consider imperfect compensator. Imperfect compensator. Fine. Process gain for the example system is 1. Time constant for the example system is 0.1. Suppose these two are perfectly known. That means Z prime equal to Z equal to 0.1 s plus 1. This is the Kp, which is 1, this is tau p, which is 0.1. The date time that is not perfectly known. This is not perfectly known to us. True value of this date time is 0.535. This is true value, and approximated value is suppose 0.3. Fine. Original value is 0.535, but we have developed the date time compensator based on the value of 0.3. Now, question is, we are using Kc value 100 because we know that our compensation is perfect. Question is, what about stability at Kc equal to 100? What about stability when Kc equal to 100? Original value is 0.535, but we are using 0.3. So, how much is the residual date time? the residual date time is 0.535 minus 0.3, that is 0.235. This is the residual date time. It is clear that the compensation is not perfect. Now, uncompensated date time corresponds to omega c naught 10 radian per minute. Fine. Uncompensated date time corresponds to Ku 1.4. At the beginning of today's class, we got these values. Fine. For the date time of 0.235, we obtain crossover frequency 10 radian per minute and ultimate gain 1.4. But how much we are using? What value of Kc we are using? Kc equal to 100, but maximum, I mean the limit is up to 1.4. So, what about stability? Unstable. System becomes unstable. Fine. Now, conclusion is be conservative in selecting the Kc value for the processes having date time. Be conservative for selecting the Kc value for the processes having date time. So, this is all about the Smith predictor and date time compensator. In the next class, we will discuss the another compensator, that is inverse response compensator. Thank you.